Hi, I'm cognitive psychologist Cristina Wilson, and I'm here in the Wissahickon Park in Philadelphia, Pennsylvania. I'm standing in front of a wooded hill slope, the kind of environment that geoscientists, like my collaborator Doug Jerolmack at the University of Pennsylvania, study natural processes like soil erosion. Much like an animal forages for food, field scientists like Doug forage for data. A field scientist has to decide where to collect data and how much data to collect to characterize an uncertain natural system. In this case, a hill slope with lots of vegetation. And importantly, the value of any additional data collected has to be weighed against the costs of collecting that data in terms of time and money. How do field scientists make spatial decisions? And how do they adapt those decisions when they're provided with real-time measurement data in the field? These are the research questions that our team is interested in answering. Studying expert field science decision-making not only has the potential to improve field science, it can also reveal fundamental principles about the human mind that evolved to explore the world and collect information. And it has potential implications for robotics. How might aerial or terrestrial robots aid in human spatial search problems? And speaking of robots, check this out. This is a robotic leg designed by my collaborator Feifei Qian at the University of Southern California. This leg was designed to mechanistically measure the strength of the soil or its vulnerability to erosion. What the leg first does is detect the ground level. Once the ground level is detected, the leg is going to intrude into the soil, where the mechanistic resistance to intrusion over time is giving a profile of the strength of the soil. Now, this is only one robot leg, but imagine a robot that had 4 of these. In theory, that robot would be able to detect the strength of the soil with every single step it took. And that robot could be autonomously deployed to collect data on soil strength in areas that it was unsafe for human scientists to go, or just to free up time for other scientific endeavors. To achieve this future of human-robot collaboration for scientific data collection, roboticists and field scientists are going to need help from cognitive scientists. After all, if we're going to teach robots where to collect data and how much to collect, and they're going to make these decisions to the satisfaction of human field scientists, we're first going to need to know, how do humans make these decisions? We asked 41 expert geoscientists to imagine that they were using a robot with legs similar to this one to study the relationship between soil strength and soil moisture, but in a slightly different environment, along a sand dune. Participants were told they would use the mobile robot Rex, pictured here, to test a hypothesis about soil strength along a dune at White Sands National Monument in New Mexico. On a dune in White Sands, there's a natural moisture gradient. A shallow groundwater table, shown by the orange dotted line here, means that the low elevation interdune areas have relatively high soil moisture, and that the moisture decreases as one traverses up a dune to the top crust. The hypothesis was that soil strength would be lowest on the dune crest, where soil was driest, and that soil strength would increase moving along the Stoss slope towards the interdune as soil moisture also increased, but that soil strength would level off as soil became more saturated nearing the interdune area. Participants were asked to test the hypothesis at a single dune. They were first provided with a cross-section of a dune transect and asked to decide on an initial sampling strategy. They had to select the number of locations to visit, the order of those locations, and how many measurements to take at each location. Taking multiple measurements at a single location corresponded to capturing variability in measurements perpendicular to the transect. Participants were instructed to be efficient and select a strategy that reflected how they would behave in similar situations in the real world. Participant sampling strategy was then executed by the robot Rex, with raw measurement data for each location being plotted one location at a time in the selected order. At any point, the participants were allowed to quit their initial sampling strategy and make a conclusion about the hypothesis, or change their initial strategy and collect additional data, either at a new or previously visited location. Participants were also allowed to collect additional data at the conclusion of their initial sampling strategy. Once participants felt they had enough data to make a conclusion, they were asked to make a judgment to either accept or reject the given hypothesis and provide a rating of judgment confidence. Unbeknownst to participants, they were randomly assigned to either receive data from an underlying distribution that supported the given hypothesis or receive data from a distribution that didn't support the hypothesis. The data that did not support the hypothesis was drawn from actual fieldwork conducted by my collaborators Feifei and Doug at White Sands with the robot Rex. They found that soil strength decreased slightly as soil became more saturated nearing the interdune, rather than immediately leveling off as described in the original hypothesis. For each hypothesis, we created a dataset of soil strength versus moisture content for 22 binned locations along the dune transect. We generated measurements at each location with a truncated normal distribution around the average soil strength and moisture. First, we will look at the sampling strategies that expert geoscientists initially selected to evaluate the hypothesis before they saw any data. Almost 90% of expert geoscientists selected locations in their initial strategy at roughly uniform intervals, which was defined as having an average spacing discrepancy of less than 1. We call this the equal spacing heuristic. 100% of expert geoscientists took a consistent number of measurements at each location in their initial strategy. We will refer to this as the magic number heuristic. There was some individual variation in the magic number selected, with most participants selecting between 3 and 5 measurements per location. Now, let's look at whether participants' sampling strategies allowed them to effectively evaluate the hypothesis. To do this, we computed the fitting error to the given hypothesis for each participant's moisture soil strength dataset. The hypothesis was treated as a piecewise linear function, and the fitting error between the data and the hypothesis was computed as the root mean squared error of this linear regression. This figure shows the trajectory of experts' fitting error by percent effective coverage of the moisture variable space. Effective coverage was determined by splitting the range of possible values for moisture into 16 intervals and computing the ratio of intervals sampled. Participants who are randomly assigned to draw from the dataset supporting the given hypothesis are represented in blue, and those randomly assigned to draw from the dataset supporting the alternative unknown hypothesis are represented in green. The dashed horizontal lines of the corresponding colors show the representative fitting error for each dataset. That is, the fitting error if all measurements in that dataset were collected. We can see in this plot that expert geoscientist sampling strategies provide data that begins to converge on the representative fitting error around 60% effective coverage. This means that the sampling strategies that geoscientists relied on allowed for efficient collection of high-value data. That is, a representative fitting error was reached by sampling just over half of the available variable space. This plot shows the distributions of final fitting error at the point where participants made a decision about the hypothesis. Again, we see good convergence of each distribution towards the representative fitting error, marked now by the vertical colored lines. Importantly, geoscientists were not provided information on statistical convergence, but still had an intuitive understanding of convergence from the graphical data. In other words, experts had an instinctive sense of when they had collected sufficient data to evaluate the given hypothesis, because most geoscientists stopped collecting data when their fitting error reached a value that was representative. Finally, let's look at the degree to which expert geoscientists adapted their initial data collection strategies in response to incoming data. Almost a quarter of geoscientists did not adjust their initial strategy at all. Among those who did adjust their strategies, almost 80% waited until their initial strategy was complete before collecting any additional data. Also among those who adjusted, almost 70% kept using the same magic number. Taken together, these results show that nearly all participants exhibited some form of anchoring to the heuristics they relied on in initial strategy selection. But this is not surprising nor unreasonable, given the general success of their heuristics at efficiently evaluating the hypothesis. With continued reliance on heuristic strategies, 80% of experts made the correct conclusion about the hypothesis for the dataset they sampled from. Amongst those who made the incorrect conclusion, all but one made a type 1 error. That is, experts sampled from the dataset that supported the given hypothesis, but made a conclusion to reject that hypothesis. Although the number of experts who made an incorrect conclusion about the hypothesis is small, there are recurring similarities amongst their decision strategy that are worth brief mention. Half of those who made an incorrect conclusion ended up relying on magic numbers of 2 or less. This increased the likelihood of undersampling and obtaining a statistical pattern of fitting error that was not representative of the source data set. Also, half of the participants who made the wrong conclusion had insufficient coverage of the variable space, less than 60%. Again, this reduces the probability of the fitting error converging to the representative value. These results highlight how heuristics that are a poor fit for an environment can lead to biased sampling decisions and flawed scientific outcomes. In the simulated scenario, the magic number heuristic and the equal spacing heuristic allowed our participants to efficiently evaluate the hypothesis. The equal spacing heuristic was effective because there was a gradual spatial gradient of soil strength and soil moisture moving from the bottom of the dune to the top of the dune. And the magic number heuristic was effective because at each location, the variables or noise in the variables was normally distributed. But these heuristics might not be as effective in every environment. Take this environment, for example. If the spatial gradient of soil moisture or soil strength along this wooded hill slope is highly nonlinear, then the equal spacing heuristic might cause us to miss out on important changes in the environment. When it comes to heuristics, it's all about fit with the decision environment. Continuing to rely on heuristics that are a poor fit for the environment can lead to biased decision making. And in field science, that means biased data collection and ultimately inaccurate working models of natural processes. New technologies like robotics can aid field scientists by providing the opportunity to adjust sampling strategies in the field in response to real-time data. And these technologies may also be able to be leveraged as decision support systems. Our research team believes that this collaborative and coordinated decision-making amongst human-robot teams is the future of field science data collection and reasoning about data. As technology grows, the structure of science and what's required of human scientists will undoubtedly change. Understanding the cognitive underpinnings of adaptive data collection decisions will help to promote the development of new technologies and workflows that optimize data foraging. And understanding these decisions will better support human scientists' most important tool, their minds. Thanks for watching. If you're interested in learning more about this research or other ongoing projects, please visit the lab website at www.radlab.us.